Howdy, welcome to Glider Project Report, Ben Hodge. Today we're going to be talking about the story, the infamous tragedy, the uprising and downfall, and all that's in between of the Big Dipper. This glider that was named after its flight pattern, where it went up very frequently and then went down very quickly, and so it was the dipping motion in the flight which preceded the name. So the mission of this assignment, our summary was to create a glider that fits within a 16-inch by 16-inch square that maintains a successful flight reaching a distance of 20 feet horizontally, which was successful in our case. And some important stipulations: it has to be hand-thrown, so no other form of propulsion outside of natural wind. So no slingshots, no rubber bands, which is unfortunate because that would have caused it to go quite a good bit further than it did. The glider must be primarily constructed of balsa wood, though through my design process I debated on using some secondary materials such as 3D printed, though realized that that would have just been a waste of time. It has to look like a glider. Hopefully that should be pretty easy for this assignment. And it can't fall apart until after reaching contact with the ground, which it actually did not fall apart, which is wonderful. For the design process, the wing shape was probably the most important part of this glider in particular. I went for a very high aspect ratio wing, so 12.85-ish, based largely off of this Federal glider over here, which was advised based off of that design. So a very long and thin wing, with a slightly tapered front end for a little bit more aerodynamics, so 15.5-inch wingspan, which is quite large and very, very close to the limit. I debated on using either a longer and thinner wing, though longer would have been quite difficult, or a thicker and shorter wing, though I decided on this more neutral zone because that would have been the most efficient route and for stability purposes is more efficacious. As for wing placement, this is where I kind of messed up initially with the initial design. The needed center of gravity needs to be in front of the wing, which I forgot and I thought it needed to be behind, which is why I placed the wing so high in the front. Obviously, based on this NASA thing that I did not look at until after my iteration moment, the center of gravity needs to be just slightly above the wing in terms of the chord length. So this is a failed first design, but it is what we went with originally, so we're going to say the other idea was either put it near the middle or near the back, and I initially decided to put it near the front, so that would change later on. That's for the tail configuration. I decided to go for a 20 to 30 inch, 30% area, not 20 to 30% area of the initial wing in terms of wing shape, which is advised by Leon Bennett of Tailspin articles. And the reason I put it so high is for higher leverage and moment due to the smaller wingspan, even though that might not have necessarily been imperative. It was more efficacious in terms of construction and simplicity. The other designs were to just put it at the same level or to put it even higher, though I debated on both and decided to come to a more neutral zone. So, as for the general sizing restraints on the other side of things, the design was focused on getting it as large as possible so that a higher aspect ratio wing could be supported. So that the higher aspect ratio wing means larger wingspan, which means that the entirety of the body of the plane has to be larger as well. So it's why it's around 15 by 15, only 1 square inch away from the not 1 square inch, 1 inch away from the size restraint, and that holds true for both the initial design and the final design, as can be seen here. So as for our final initial design, we were left with this, with the unfortunate wing placed in the beginning, and their original construction was made out of cardboard prototype, in which case all the wing pieces, the dowel was used originally, these wings were just taken off with hot glue originally. And with the initial testing, results were tragic. It would constantly stall, and it wouldn't even reach 10 feet. It was remarkably unstable as well. It was kind of hard to tell because of how high up it was going. So the issue that I determined was that it was a center of mass problem, which can be seen up here with this diagram from NASA. So the solution to this was very scientific. I just said, I'll just move the wing back a little bit, and to a very scientific depth of that looks right for about where a wing should be. And it worked. It actually worked very well. Just putting some plate on the front, and it equaled out the center of mass to be just a little bit, about an inch in front of the quarter chord. And it can be seen in this test flight right here. So the actual final design ended up looking something like this, with the Play-Doh on the front and some tape on the back due to some construction issues with the pre-flight testing. So under the calculations, the center of gravity was about an inch in front of the quarter chord, as I previously mentioned. This was done to increase stability as much as possible without causing frequent nosedives. Potentially moving this distance to a little bit shorter, closer to the quarter chord, might have caused some more sustaining flight as opposed to the nosediving that eventually did happen due to it being called the Big Dipper, and I guess being more massive in the front. As for the coefficient of lift approximations, velocity was obtained via tracker, determining a distance and how quickly it went across that distance. As for the wingspan, it was calculated via SolidWorks, and the area was calculated using NASA's wing area diagram from Glenn Research Center, which is very helpful in this assignment. The weight was approximately half a pound, based off of just general flight data, and the rest of the variables kind of helping figure that out. So, coefficient of lift was determined to be 1.8149 e to the negative 4. That's going to be calculated here on this paper. And we use that number to put into coefficient of drag, which paired with our aspect ratio that was calculated with the initial design, and E being approximated to 0.90. This was plugged into this formula right here to get a coefficient of drag 3.90351 e to the negative 10, which is quite good. And we can see that on flight day, it performed quite well. That flight was about 40 feet. Due to some pre-testing, it was actually about 55 feet was the best tested, which is quite good. Unfortunately, we did not reach that on flight day, but I was going against the person who had glided that went 80 feet, so it didn't really matter. Closing remarks and further improvements. The Big Dipper was a phenomenal glider. However, it needed some improvements. Maybe more precise mass measurements, I think, would be the largest in terms of the Play-Doh in the front. In addition, sanding it would cause for a little bit more aerodynamicness, so I don't know how much that would have actually impacted the ending distance by a ton, since it is a glider and it is made of light balsa wood. And of course, more durable tail construction, because this is unacceptable in terms of real-world flight, and this would be pretty bad. So yeah, that's all. The sources that I used were largely from NASA and the Federal Aviation Administration, or FAA. I did take some third-party stuff, but it was only one article, just for the sake of the tail wing. Thank you so much for watching, and have a great day. Bye-bye.